Okay, so we're going to be solving this question right here from Midterm 1, version A, and I rewrote it on the board here. The Ka of 1 molar aqueous monoprotic weak acid is 2.3 times 10 to the negative 6. And they want us to solve for the concentration of A, the concentration of H+, the pH, the percent dissociation, and the SO3 2 minus Kb. So let's get started. Okay, so this is the only information they give us, but it's actually a lot of information because they tell us it's a monoprotic acid. That means a weak acid. That means that it only one H+ ion is involved with it, and it doesn't completely dissociate in solution. They also tell us it's aqueous, so we know it's in solution. And they tell us our Ka. So if we want to write that in all this stuff, we'll write down it's a weak acid. It has one H+ involved. Not one H+ literally, but in the ice chart way involved. And also the Ka is equal to 2.3 times 10 to the negative 6. So the best thing is to kind of draw the information first off, what useful information you can find. The last bit of information that we can draw from this sentence is that the solution is 1 molar. The weak acid solution was 1 molar. Weak acid solution. Okay, since they don't tell us the actual substance being used, the actual weak acid, we can start off with a generic weak acid formula, which would look something like this. This representing your weak acid, this representing dissociation, your H+ ions, and your A- ions, okay? So this is basically the equation. And they tell us our initial value, which is 1 molar of the HA. However, we're not looking for our initial, we're looking for our equilibrium values. So the only way to find equilibrium values is to use an ice chart. So we're going to start off with initial, change, and equilibrium. So from the sentence, the Ka of 1 molar aqueous monoprotic acid is given. So we can determine that there's 1 molar of the initial weak acid, and there is 0, or there are 0 H+ ions and 0 A- ions, or conjugate base ions, because nothing is dissociated yet. So if we don't really know how much, what molarity dissociates, but we know that it equals back and forth. It forms an equilibrium. So whatever is lost on this side has to be gained on this side, whatever moles basically. Because if you lose, say you lost 1 mole in here, then it'll break up into 1 mole and 1 mole. Or if you lost 2 on this side, it would break up into 2 and 2. So it would be 2 and 4. But so essentially, we're losing an X and we're gaining an X here and we're getting an X here. That's the molarity. I'm not writing molarity for everything else because it'll get excessive. But so now we can simplify, and it becomes 1 molar minus X, and this is X, and this is X. So, and the relationship between Ka and your equilibrium is equal to Ka is equal to the H+ ions times the A- ions, or molarity, the concentration actually. The H+ concentration, A- concentration over the HA concentration. So we have our numbers here for our concentrations, and we have our Ka up here. So we can actually fill this in. So I'm going to fill in with a different color. Let's do green. Okay. So this number, so let's actually just fill in here. So H+ is X, okay? We get that from our ice chart. A- is X. that's also from our ice chart. And the last value we get from our ice chart is the HA, which we put down as 1.00 minus X, okay? And that's a concentration, so we use the brackets to distinguish or to represent concentration. Where do we get Ka from? We get Ka from our equation. It's given to us. And also written down here in our information box. So let's plug that in. 2.3 times 10 to the negative 6. So remember, we're trying to solve for A minus and H plus. So the way we solve for this is by actually, let's see, multiplying this out actually. Let's do that. So we're actually going to get x squared over 1.00 minus x is equal to 2.3 times 10 to the negative 6. And our whole goal is to solve for x so that we can plug it back into here and determine our concentration. So let's solve for x. Solving for x, we can take the square root. Actually, first before that, we can actually use the, if we wanted to actually solve for this, we'd have to use a quadratic. In order to get around that, we're going to make an assumption. We're going to make an assumption that this x right here, which is the dissociation, is so small, the H plus dissociation, is so small that we can kind of ignore it in a way. So we're going to basically simplify it down to even further. X squared over 1 is equal to 2.3 times 10 to the negative 6. Now, this assumption we'll have to check later on, but we can do it right now to make things simpler. And so now here's the actual math behind it. Okay, we're going to solve for x. So the way we're going to do that is we're going to take the square root on both sides in order to get rid of the x squared, and we are going to get x over the square root of 1 is 1, so we'll just get 1. And this square root we'll actually have to plug into our calculator. Okay, so we're going to actually plug this number into our calculator in order to solve. So we're going to get the square root button. There we go. 2.3 times 10 to the negative 6, because that's our number. And we're going to write down our answer, which is, we'll put it into scientific notation by doing it there. 1.517 times 10 to the negative 3. Okay, and basically the denominator is 1, so we can confirm, we'll write it right here, we'll confirm that x equals 1.52 times 10 to the negative 3. And this is one of the, we haven't found our answer yet, but this is one of the things we were looking for. So what can we do with this x value? We can plug it back into our ice chart here, here, and here to find our H plus and our A minus, which is what our questions are. So if you plug in this into x, you're just going to get this number back. So we're going to do that, and we'll write our answer over here because we basically found our answer already. So plugging this back into here, remember that this is concentration. We're plugging it back into concentration of the A minus. So our concentration is equal to 1.52 times 10 to the negative 3rd, and it's in molarity. So we're going to use molarity. Don't forget your units. Now, the A minus dissociates just as much the H plus, so it's also 1.52 times 10 to the negative 3 molar. Okay, so that's how you find, we've just found the H plus concentration and the A minus concentration given this information by using an ice chart. But we've only answered 2 of our 5 questions. So the next question is, how do we find pH? Well, the generic form for finding pH is pH is equal to the negative log of the H plus concentration. Okay. Now, the H plus concentration, we just solve for that. So we can take this number and plug it in. So we'll do negative log of 1.52 times 10 to the negative third, and that's concentration. So we're going to take our calculator and do the same thing. So we're going to do, let's get this close, negative log of 1.52 times 10 to the negative third. And we solve for that, and we get 2.8 as our answer. Right there, 2.8. So now we can write that down. What's pH? So our pH is equal to 2.82. And that's one of our answers. So now we just write it up here, 2.82. Percent dissociation is actually basically the same thing as doing our assumption check. Because remember we assumed that the 1 minus x was simply 1, which meant that the dissociation of H plus ions right here was such a small amount that it was almost insignificant. So, or basically insignificant. So now we're going to actually do our test and our percent dissociation at the same time. So the way this works is we take our percent dissociation, or actually, so the assumption check is basically your H plus concentration divided by your HA concentration. That's just the generic form, times 100. Okay, so that makes it a percentage. So we take our H plus concentration, which is given here. So we plug it in. Let's solve for that. So it's 1.52 times 10 to the negative 3, and that's a concentration. That's our H plus concentration. And our HA concentration was 1. All right? So that was 1 was our concentration for our initial HA concentration. Now we're going to multiply by 100, and we are going to get our answer. So now let's use a calculator, and we're going to do 1.52 times 10 to the negative third, okay, divided by 1, which is 1, times 100. You didn't really need a calculator to do this, but you get the idea. So let's put it back in a standard form, and you'll be able to see that the answer is 0.152%. Okay? Now, that's our percent dissociation. They're looking for percent dissociation of your H plus, because that's the main thing that matters when it comes to pH and things like that. So the percent dissociation was 0.152%. And for the assumption check, when your assumption is good, so let's write good assumption, because it is, a good assumption has a percent dissociation of less than 5. Okay, so there you go. I'll just put an X there to show the percent dissociation. Okay, so that means that a good assumption has a percent dissociation below 5%. So this is definitely below 5%. It's really small. So that means that our assumption was good, and this is also our answer for percent dissociation. So we'll write this up here. We'll keep with the red, I guess, because that's the mode we're going with, or the standard we're going with. So 0.152%. Don't forget your percent. Okay, so we're going to look for the Kb of SO3 2 minus. Now we go to our chart. Our chart gives us Ka values, but we can use those to find Kb values. If we look on the chart, we find H2SO3, and there are actually 2 Ka values given to us. The first one is 1.4 times 10 to the negative 2, and the second one is 6.3 times 10 to the negative 8. Now, the reason why we get 2 values is because there are two H plus ions in H2SO3, and they each dissociate at different Kas. So we're actually looking for the SO3 2 minus Kb, which is the second ion being released. So I'm going to go over here and basically explain this again more clearly. Okay, so we start off with H2SO3, and this will dissociate into H plus plus HSO3 minus. Okay? And this is the first dissociation. The second one begins with HSO3 minus 3, and it becomes H plus plus SO3 2 minus. So they give us both values on this. They give us the Ka for this one, which is Ka1, and this is Ka2, okay? But remember, we're looking for Kb. So we know the Ka we're looking for is the second one, because that relates to this equation. So that the Ka is equal to 6.3 times 10 to the negative 8. But how do we get Kb? Ka times Kb is equal to Kw. Okay, this is the Ka for water, or the Kb for water, and we can basically use this relationship in order to solve. So we're going to do Kb times 6.3 times 10 to the negative 8 is equal to 1.0 times 10 to the negative 14, because that's the Kw for water. So now we're going to divide on both sides. The 6.3 times 10 to the negative 8 divided by 6.3 times 10 to the negative 8. There we go. This is a point. That's a point. So then this will cancel, and we'll go to our calculator to solve this next portion right here. Okay, so now we'll take our 1.0 times 10 to the negative 14, and we will divide it by 6.3 times 10 to the negative 8. And that's going to give us, let me write it down. It's going to give us, our Kb value is going to be equal to 1.59 times 10 to the negative 7. Okay? And this is the Kb value, so it has no concentration. Sorry, no units, because it's not a concentration, it's just a number basically. It's a rate, almost. So this is our final answer for the Kb of SO3 2 minus. So we're going to write this over here. It's 1.59 times 10 to the negative 7. So now, after all that, we've pretty much solved everything that we've been asked for. The A minus concentration, the H plus concentration, the pH, the percent dissociation of the H plus ions, and the Kb of SO3 2 minus. So that's it.